and welcome back to Probability and Statistics. For today, we're going to discuss probability, the terminologies, and its examples. Before we dive into terminologies and its examples, we'll have a recap first on counting and sets. So we've discussed in counting and sets and notations, then diagrams, De Morgan's law, products of sets, inclusion-exclusion principle, rule of product, combination, and permutation. For today, we're going to know the definition of sample space, event, and probability function, be able to organize a scenario with randomness into an experiment in sample space, and be able to make basic computations using probability function. So here is the probability cast list. First one is experiment. When we say experiment, this is a repeatable procedure with well-defined possible outcomes. Also have sample space, the set of all possible outcomes. We usually denote the sample space by big omega or sometimes by S. We also have event, a subset of the sample space. We also have the probability function, which is a function giving the probability for each outcome. We also have the probability density, which is a continuous distribution of probabilities. We also have the random variable, a random numerical outcome. Later in this course, we'll learn about probability density and random variable. But for now, let's take a look at some examples of probability. So let's say, for instance, we will toss a fair coin. So our experiment here will be toss the coin and report if it lands heads or tails. So that will be our experiment. For our sample space, we have the big omega, which will be equal to heads and tails, or we will denote heads as H and will denote tails as T. Okay. So for probability function, since we will report if it land heads or tails, our probability function will be probability of heads or P of H, and which is equals to 0.5, and P of probability of T or P of T is equals to 0.5. So that's an example of experiment, sample space, and probability function. Another example is, let's say for instance, we will toss a pair of coin 3 times. So our experiment will be toss the coin 3 times and we'll list the results. Our sample space here will be big omega will be equal to HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. For our probability function, we'll have each outcome is equally likely with probability of 1 over 8. Each outcome, so this is an outcome. Let's say for instance HHH, that's an outcome. So since this is 1, 2, 3, 4, 5, 6, 7, 8 outcomes, HHH is 1 over 8. The probability of HHH is 1 over 8. Okay? So that's an example of experiment, sample space, and probability function. For sample spaces, we can put the set of outcomes and probabilities into a probability table. So let's say for instance, so like what I've said earlier, so example, this sample space, so we have here the outcomes, and then the probability will be 1 over 8 for HHH, 1 over 8 for HHT, 1 over 8 for HTH, and so on and so forth. Okay, so we can represent our outcome into probability table. Another example here is, let's say for instance, we will measure the mass of a proton. So our experiment here will follow some defined procedure to measure the mass and report the result. So our sample space here will be big omega will be equal to 0 until infinite. Okay, so example, in principle, we can get any positive value. Okay, we can get any positive value. It starts from 0 and infinite. Okay, in probability function, since there is a continuum of possible outcomes, there is no probability function. Instead, we need to use a probability density, which we will learn later in this course. Okay, so that's another example. For example number 4, let's say for instance taxis. which is an infinite discrete sample space. So our experiment here will count the number of taxis that pass 77 mass average during a class. So our sample space here will be big omega, which will be equal to 0, starting from 0 until an infinite value. So this is often modeled with the following probability function known as the Poisson distribution. Don't worry about mastering the Poisson distribution just yet. So to say Poisson distribution, we have the probability of k is equals to e raised to negative lambda multiplied by lambda raised to k over k factorial. Okay, where lambda is the average number of taxis. Okay. So another example is we can put this in a table. So we can put the Poisson distribution on table. So the outcome would be 1, 2, 3 until k until infinite. So the probability for the zero outcome is e raised to negative lambda. For 1, e raised to negative lambda multiplied by lambda. For number 2, e raised to negative lambda multiplied by lambda squared divided by 2. For number 3, e negative lambda multiplied by negative lambda raised to 3 divided by 3 factorial until k. So e negative lambda multiplied by lambda raised to k divided by k factorial. So the question here is, accepting that this is valid probability function, what is summation of the lower limit k is equals to 0 and until the upper limit infinite, which will get the summation of e raised to negative lambda multiplied by lambda raised to k over k factorial. So the answer for this would be, this is a total probability of all possible outcomes. So the sum equals to 1. So note that this follows from the Taylor series. So the Taylor series defined as e raised to lambda, which is equals to summation of lower limit n is equals to 0 with the upper until upper limit infinite by getting the lambda n over n factorial. Okay, there it is. So later on, later in this course, I will discuss the Poisson distribution. So don't worry if you aren't able to understand this example. But that's how we represent Poisson distribution in probability table. Okay, so we also have here a sample of 2 dice. So we will choose of sample space. So suppose you roll 1 die, then the sample space and probability function are, so we have the outcome 1, 2, 3 until 6. So since dice will consist of 1 to 6, no? So its probability will be 1 over 6. Each of the outcome will be 1 over 6. So now suppose you roll 2 dice, which should be the samples, what should be the sample space? Here are the 2 options. So first we will record the pair of numbers showing on the die. So first die and second die. And then we will record the sum of the numbers on the dice. In this case, there are 11 outcomes. We have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these outcomes are not equally likely. Okay? So each of the 36 outcomes is equally likely. Why 36 outcomes? For the probability function, we will make a 2-dimensional table, which is shown below, with the rows corresponding to the number on the first die. The columns, the number on the second die, and entries, the probability. So here is the 2 dice in 2-dimensional table. So 1, 1, so 1 over 36. So 2, 2, 1 over 36. So the probability is 1 over 36 for all the outcomes in 2-dimensional. So in the second case, we can present the outcomes and probabilities in our usual table. Okay, so in a 1-dimensional table, we can represent that. So the outcome will be 2, 3, 4, 5, 6, 7, 8, 9, 10 until 12. So for number 2, we can only get 1 over 36 probability. Okay, for number 3, we have 2 over 36 probability. For number 4, 3 over 36. For number 5, 4 over 36. For 6, we have 5 over 36, and so on and so forth. Okay, so think, what is the relationship between the 2 probabilities tables above? we'll see that the best choice of sample space depends on the context. For now, simply note that given the outcome as a pair of numbers, it is easy to find the sum. Note that listing the experiment, sample space, and probability function is a good way to start working systematically with probability. It can help you avoid some of the common pitfalls in the subject. We come now to event. So an event is a collection of outcomes. Example, an event is a subset of the sample space, which is denoted with big omega. So this sounds odd, but it actually corresponds to the common meaning of the word. Okay. So example of an event. So using the setup in example 2, we would describe the events that you get exactly 2 heads in words by denoting E, which is equals to exactly 2 heads. Written as a subset, this becomes E is equal will be equal now to HHT and HTH and EHH, since we are only getting exactly 2 heads. You should get comfortable moving between describing events in words and a subset of the sample space. The probability of an event E is computed by adding up the probabilities of all of the outcomes in E. In this example, each outcome has probability of 1/8. So we have the probability of our event is 3/8 since we have 3 outcomes. Okay? So that's an example of an event. So the definition for a discrete sample space, when I say a discrete sample space, is one that is listable. It can be either finite or infinite. Okay? So let's say for instance an example for discrete sets, we have H and T for head and tails. We have 1, 2, 3. We have 1, 2, 3, 4. We have 2, 3, 5, 7, 11, 13, 17. So are all discrete sets. The first 2 are finite and the last 2 are infinite. So here we have head and tails and 1, 2, 3. That's the finite discrete set, and 1, 2, 3 for until ... and 2, 3, 5 until ... That's infinite. Okay. So for example, another example, the interval x is greater than 0 but less than 1. So the interval is not discrete, rather it is continuous. Okay, so ranging from 0, the x is ranging from 0 to 1. That is not discrete, so rather it is continuous. We call that continuous value. So the probability function, so careful definition of the probability function. For a discrete sample space S, a probability function P assigns to each outcome little omega. So please note that this W-like symbol is also known as little omega. A number probability of little omega, called the probability of little omega, P must satisfy 2 rules. So the first rule will be the probability of little omega should be in the interval or should be between 0 and 1. So that's the first rule. The second rule would be the sum of the probabilities of all possible outcome is 1. So that means that the probabilities of the sum of all possible outcomes should be equal to 1. So in symbols, rule 2 says if our sample space S is equals to little omega 1 until little omega n, then the probability of little omega 1 plus the probability of little omega 2 plus until plus the probability of omega n, it should be equal to 1. Or using the summation notation. So when we say summation notation, sorry, I haven't introduced summation notation. So when we say summation notation, we are getting the sum of, sometimes summation notation is denoted as loop in mathematical symbol. Okay? Summation notation, the lower limit, so that means our summation will start at j is equals to 1 until the upper limit is n. Okay? So inside that summation notation, we can get the probability of little omega j. So from 1 to n. So we'll get the sum of the probability of little omega j. That should be equal to 1. So that's the probability function here. So the probability of an event E is the sum of the probabilities of all the outcomes in E. That is the probability of event, which is equals to summation of little omega is a set of events. So we'll get the probability of little omega. So check rules 1 and 2 on example 1 and 2 above. So example 7, so flip until heads. So suppose we have a coin with a probability P of heads and we have the following scenario. Our experiment in this example will be toss the coin until the first heads and we'll report the number of tosses. For the sample space, we have the big omega, which is equals to 1 to 3 infinite. So 1 to 3 until infinite. Our probability function here will be probability of n is equals to 1 minus p, or the probability of heads, raised to n minus 1 multiply the probability of heads. So our first challenge here is to show the sum of all probabilities, which should be equals to 1. Okay, so our second challenge is to justify the formula for probability of n. We'll do this soon. The previous toy example is an uncluttered version of a general class of problems called as stopping rule problems. So this is called as stopping problems, okay? So a stopping rule is a rule that tells you when to end a certain process. So in the toy example above, the process was flipping a coin and we stop after the first heads. So a more practical example is a rule for ending a series of medical treatments, such as a rule could depend on how well the treatments are working. So best example now is the clinical trials on COVID-19 vaccine. So if the researchers or the scientists gained a probability of greater than 50% in their clinical trial, or much better if 70% up, so they will stop the clinical trial. That means that the COVID-19 vaccine is already met the certain conditions or the certain efficiency or efficacy of vaccine in terms of curing or preventing COVID-19. Such a rule could depend on how well the treatments are working, how the patient is tolerating them, and the probability that the treatments would continue to be effective. One could ask about the probability of stopping within a certain number of treatments or the average number of treatments should expect before stopping. Okay, so that's the stopping rule problem. So that's the best example for that is the clinical trials for COVID-19 vaccine. So for some rules of probability, let's say for instance, for events A, the left and right contained in a sample space. So the rule number 1 would be the probability of A complement should be equal to 1 minus probability of A. The rule number 2, if left and right are disjoint, then the probability of left union R should be equal to probability of left plus probability of right. In rule number 3, if left and right are not disjoint, we have the inclusion-exclusion principle, which denotes probability of left union right is equals to probability of left plus probability of right minus the probability of L intersection of right. Okay, so we visualize these rules using Venn diagrams. If you will recall, the inclusion and exclusion principles is just removing the duplicate in the overlap of union of two sets or two subsets. We visualize this using Venn diagram. So our sample space here is equals to A union of A complement. So there's no overlap. So that's the rule number 1. So if our sample space, so we all know that the our outcomes or our probability should be equal to 1 based on our previous discussion, no? So if we deduct the probability of A in 1, we could get the A complement. Okay, so here. We also have the rule number 2. If L and R are disjoint, then the probability of left union right is equals to probability of left plus probability of right. Here is the L union of R but no overlap. So we're just getting the sum of the probability of left and the sum of probability of right. So in the last rule, If L and R are not disjoint, we have the inclusion-exclusion principle, okay? So we'll get the left union R with overlap, but will conduct an inclusion-exclusion principle. Will deduct the duplicate. Here is the duplicate. Okay, so the overlap. We will deduct the overlap. So we can also justify them logically. So for rule number 1, A and A complement split sample space into two non-overlapping regions. Since the total probability of sample space is 1, this rule says that the probability of A and the probability of not A are complementary. Example, sum to 1. Okay, for rule number 2, left and R or left and right split L union of R into two non-overlapping regions. So the probability of L union R is split between probability left and probability of right. Okay, so for rule number 3, in the sum of probability left and probability right, the overlap of probability of left intersection R gets counted twice. So the probability of left plus probability of right minus the probability of left intersection R counts everything in the union exactly 1. So think, rule number 2 is a special case of rule number 3. Why? So in rule number 2, we are just splitting our sample space into 2 by getting the probability of left and right. If we sum the probability of left and the probability of right, we can get 1. In rule number 3, we represent it in an overlapping situation. So we should conduct an exclusion-exclusion principle. But the principle of rule number 2 and rule number 3 are the same. Another example, if the probability of an even number is 0.6, what is the probability of an odd number? Since being odd is complementary to being even, the probability of being odd is 1 minus 0.6, which is equals to 0.4. So simple example of rules of probability. If our sample space is divided into 2, so if we get the probability of the first event, so we can just deduct the probability of that event to 1. So we can get the probability of the second event. Okay, so let's redo this example a bit more formally so you see how it's done. First, so we can refer to it, let's name the random integer x. Let's also name the event x is even as A. Then the event x is odd is A complement. We are given that probability of A. Therefore, the probability of A is equal to 0.6. Therefore, the probability of A complement should be equal to 1 minus 0.6, which is the probability of A. So that will be, the probability of A complement will be equal now to 0.4. So for example number 9, consider the two events. So A, our first event or the A event is x is a multiple of 2 and our B event is x is odd and less than 10. Suppose the probability of our first event, which is A, the probability of A is equals to 0.6, then the probability of B is equals to 0.25. So what is A intersection of B? So another question, what is the probability of A union of B? So the answer for this is for number 1, since all the numbers in A are even and all the numbers in B are odd, these events are disjoint. That is A secting B, which is equal to empty set. Okay. For number 2, since A and B are disjoint, so the probability of A union B is equals to probability of A plus probability of B, which is equals to 0.85. Another example, let A and B and C be the events in X is a multiple of 2, 3, and 6 respectively. If the probability of A is equals to 0.6 and the probability of B is 0.3 and the probability of C is 0.2, what is the probability of A or B? And the answer for this is note these two things. No, first we use the word or, which means union, A or B, or which is equals to A union of B. Second, an integer is divisible by 6 if and only if it is divisible by both 2 and 3. So this translates into C is equals to A intersection of B. So the inclusion-exclusion principle says the probability of A union B is equals to probability A plus B minus the probability of A intersection of B is equal to 0.6 plus 0.3, so that's 0.9 minus 0.2, so that will be equal to 0.7. Okay, so the probability of A or B is 0.7. So that's it for the probability, the terminology, and its example. So thank you very much for listening for today. So see you on the next video. Thank you.